To find the solution when you're asked to factor, we want to go through each term and check for a greatest common factor, and then we need to check to make sure I have an even number of terms. In these problems, I have an odd number of terms in 1, 2, and 3. A term is a number that's separated by, or is an expression separated by addition or subtraction. So each of these examples represents a trinomial because there are 3 terms. I have in number 1, x squared is my first term, 5x is my second term, and 6 is my third term. In order to factor by grouping, I need to have an even number of terms. I want to turn your attention to an example that we did before. When we applied the distributive property twice in this previous slide, notice that here in this third step, we combined the terms 2x and negative 15x. When we did those, we've got negative 13x. This solution in this problem was a trinomial because I had 3 terms, 6x squared, negative 13x, and minus 5. When I'm done factoring, I'm going to end up with an expression that looks like this. It will be a product of simple terms that have no common factors in them. 3x and 1 have no common factors. 2x and minus 5 have no common factors. So when I am done factoring this trinomial down here, I am going to get a product of numbers and grouping symbols. And in order to do that, I need to back up this multiplication process and instead write it as a division process. So my first step is going to be to split my trinomial into an expression that's equivalent that has 4 terms. So I need to split my middle term into 2 numbers that add to be my middle term, which is bx. So what I'm going to do in the example that we're working on down below is I'm going to start by splitting the middle term of my trinomial into 2 terms that add to be that expression. In this slide, we're asked to factor each expression. Each of these expressions is a trinomial of the form ax squared plus bx plus c. This is called a quadratic trinomial because it has a degree of 2. That means our highest exponent is 2. So each of these terms is a trinomial, but only numbers 1 and 2 are quadratic trinomials. Notice that in number 3, we have an exponent of 3. That's going to change the steps that we use to factor slightly, but it's okay because when we get to number 3, I'll clarify our steps. In order to factor each of these trinomials, I'm going to have to write them with 4 terms instead of 3 terms. That means I'm going to split my middle term into 2 terms using a diamond problem so that I can reverse the distributive property and end up with a factor pair like this, that when I apply the distributive property, I would end up with the original expression in number 1. So in order to split my 5x term, I'm going to write a diamond problem. My diamond problem is going to have a times c on top and b on the bottom. So let's start by identifying a, b, and c in number 1. A is the number being multiplied by x squared. Since it doesn't have a coefficient, the number 1 must be what's being multiplied by x squared, since 1x squared equals x squared. B is equal to 2, or is equal to 5, because 5 is the coefficient of the middle term, and c is equal to 6, because 6 is the constant term that doesn't have a variable in it. I didn't like my arrow, so we wrote it again. I also want to make a note of the product a times c. In this problem, a times c is 1 times 6, which is 6. So in my diamond problem, I'm going to write the number 6 on top. The number on the bottom of my diamond problem is 5, That's because my sum has to add up to be 5x, and 5 is my b. So the solution to my diamond problem will be the two numbers that multiply to be 6 and add to be 5. The way I figure that out is by considering the different factors of 6. I can either do 1 times 6 or 2 times 3, and considering which of those add up to be 5. That will be our bottom pair because 2 plus 3 is equal to 5. So my first step is to split my middle term into two factors, or into two terms with coefficients 2 and 3. That gives me 2x plus 3x. I bring down the other terms in my expression. So I've just created an equivalent expression where if I were to combine 2x and 3x, I'd get my original expression, x squared plus 5x plus 6. I don't want to combine them now because what I want to do is split them into these four terms. Now I'm going to factor these four terms by grouping pairs of terms and dividing out the greatest common factor. The greatest common factor of x squared and 2x is a single x because that's the factor that they both have in common. If I divide x squared by x, I'm left with a single x. And then if I divide 2x by x, I'm left with just the number 2. I'm going to write a plus sign, and now I'm going to factor the greatest common factor from my second pair of expressions. The GCF of 3x and 6 is 3. That's because 3 divides both 3 and 6 evenly. I'm going to divide out my greatest common factor. 3x divided by 3 is just x, and 6 divided by x is 2. Notice what happened here. I resulted in two identical factors. The reason that I got these identical factors is because I used the AC rule to split my 5x into two terms that multiplied to be 6 and added to be 5. If I had chosen any other combination, for example, 1 and 6, when I factored out the greatest common factor, I would not have had an identical factor pair of x plus 2. The reason we do it in this way is that if you look, I now have a new common factor of x plus 2. I can rewrite that now, dividing out that common factor. If I divide out my x plus 2 that's in each expression, what I'm left with in my first term, x times x plus 2 divided by x plus 2 is just x. 3 times x plus 2 divided by x plus 2 is just 3 because any number divided by itself is 1. Right, and now I have a factored expression. X and 2 and x and 3 have no more common factors, and my entire expression has been written as a multiplication problem. So I have successfully factored this expression. For example 2, I have a similar, I'm going to repeat the same process, but I no longer have my a equals to 1. Notice that when I had a equals to 1, the two numbers that solved my diamond problem were also my two factors in the end. That will always happen when a is equal to 1. When a is not equal to 1, I need to be very careful to apply the AC rule, or my diamond problem will not result in a solution, or if it does, that solution will not result in a perfect common expression when I factor my groups. So I want to identify A, B, and C. Let me move these first ones out of the way so they don't overlap with my new problem. In this problem, A is equal to 6, B is equal to negative 19. Note the sign here goes with coefficient. And C is equal to 10. That means A times C is equal to 6 times 10, which is 60. So when I write my diamond problem, my product AC is going to be 60, and my sum is equal to B, which is negative 19. So negative 19 will be on the bottom of my diamond problem. I want to look for two numbers that multiply to be 60 but add to be negative 19. So I'm looking for factors of 60 that are 19 units away when I subtract them. Since my product is positive and my sum is negative, both of my factors must be negative. So I consider each of the factors that multiply to be negative 60. Negative 1 times 60. Oh, negative 60. Negative 2 times negative 30. Negative 3 times negative 20. Keep in mind, as I'm writing each of these, I'm mentally going through and adding them together. Negative 3 plus 20 is negative 23. That's not going to be our solution because it doesn't add to be negative 19. Negative 2 and negative 30 is negative 32. Negative 1 and negative 60 is negative 61. None of these equal negative 19, so I'm keeping going. 60 can also be written as 4 times 15. So if I do negative 4 times negative 15, I am actually now 19 apart. Negative 4 times negative 15 is negative 60, is positive 60, but negative 4 plus negative 15 is negative 19. So this is our factor pair. I'm going to split my bx term into two terms that add to be negative 19x, and their two coefficients are going to be negative 4 and negative 15. Now, in my original problem, my variable is x, so each of these terms has an x. It's also good to write your negative numbers in parentheses. I bring down the rest of my expression. And now I've split my trinomial into 4 terms that I can factor by grouping. I group my first 2 terms and I group my second 2 terms, and I'm going to divide out the greatest common factor of each pair of terms. The biggest number that divides both 6 and 4 evenly is 2. And the biggest number of variables that divides both x squared and x evenly is a single x. If I divide 6x squared by 2x, 6 divided by 2 is 3. X squared divided by x is x. If I divide negative 4x by 2, I get negative 2. X divided by x is 1. So just 3x minus 2 is my term that's in the grouping symbols. Plus, I want to find the factor that I can undistribute. Notice that my leading that the coefficient of x here in the grouping symbols, you want to try to keep it positive. So I'm going to divide by a negative number. My GCF is going to be negative 5. That's because 5 divides 15 and 5 divides 10, but I also want to wind up with a positive x term in my parentheses. So I'm going to divide both terms by negative 5. When I do, negative 15x divided by negative 5 is positive 3x. And positive 10 divided by negative 5 is negative 2 minus 2. Notice that I got the exact same factor in each pair of terms. That's because I used the AC rule. If I'd chosen any other pair of factors that multiplied to be 60, I would not have gotten an identical common factor when I divided unless those two factors added up to be negative 19. So it's a little complicated, and without using the AC rule in a diamond problem, you have to do a lot of guess and check, and it can be very frustrating. So that's why I'm teaching this method, just so you know, there is a method to my madness. The last step here, though, because we're not quite done, is I need to divide out my common factor. My common factor is 3x minus 2. If I divide that from each of my terms in the previous step, what I'm left with is 2x minus 5. So my final factored product is the group 3x minus 2 times the group 2x minus 5. And if I were to apply the distributive property 2 times, I would get back to that original expression, 6x squared minus 19x plus 10. My last example is a little bit different. I do have a trinomial, and I am going to need to split my middle term in order to factor this group. However, I have an exponent other than 2 as my highest exponent. That tells me that I need to look for a common factor between all 3 terms before I get started. It's a good idea to do that early on in the process, because even if you don't have an exponent of 3, if your 3 terms in your trinomial have a common factor that's just a number factor, you're going to want to factor it out because you don't want any common terms in our final answer. So I am looking for the greatest number that divides negative 2r to the power of 3, negative 9r squared, and negative 9r. In this case, all 3 terms contain a negative, and all 3 terms contain an r, but there's no common number factors. So I'm going to divide each term by negative r. Negative 2r to the power of 3 divided by negative r gives me positive 2r squared. If I multiplied negative r times 2r squared, I would get negative 2r cubed. Next, if I divide negative 9r squared by negative r, I'm left with negative 9 divided by negative 1 is positive 9. R squared divided by r is equal to a single r. Negative 9r divided by negative r is positive 9. Now, if I look inside my group, I see that I have a trinomial, and it's a degree 2 trinomial. So I can identify A, B, and C from this group. I only consider what's inside my grouping symbols when I do this step. My A is equal to 2. My B is equal to 9. And my C is equal to 9. A times C is equal to 2 times 9, which is 18. So when I write my diamond problem, I want to have my product of AC on top. And my sum is equal to B, which is equal to 9. Notice I don't write 9x, I just write my 9. It's a positive 9. I consider all my factors that multiply to be 18. 18 is 1 times 18, and it's also equal to 2 times 9. It's also equal to 3 times 6. 4 does not divide 18, neither does 5. And if I divide 18 by 6, I'm back to 3 times 6. So I'm done finding all my factor pairs. And if I look, I can see that the one that adds to be 9 is my last option. 3 plus 6 equals 9. So that means my solution to my diamond problem is 3 and 6. So I'm going to go ahead and I'm going to rewrite my expression. So I split my plus 9r term into 3r plus 6r. I bring down my outside factor of negative r, and I just bring it along for the ride. This is going to be 2r squared plus 3r plus 6r. I'm going to write them both because since I'm writing in different colors, I don't have to tap it twice, plus 9. Now I have 4 terms that are equal to my original expression, and I can divide out my greatest common factor of each pair of terms. At each new step, make sure to bring down your outside factor, your outside greatest common factor of negative r. In this first pair, the GCF of 2r squared and 3r is r. If I divide out my common r, 2r squared divided by r is just 2r. 3r divided by r is just 3. The greatest common factor of 6r and 9 is 3, since 3 divides both 6 and 9 evenly. 6r divided by 3 is 2r. 9 divided by 3 is 3. And you can tell that I did this correctly because I wound up with the exact same factor pair in both of my groups. Last but not least, I divide out my greatest common factor, which is now the pair of the expression 2r plus 3. When I divide each term by my common factor, what I'm left with in my first group was just r, and in my second group, I'm left with 3. So this is my final factored expression.